Okay, we looked at units and dimensions. Now we're just going to talk about a little more basic math here to help you out with your physics homework. First off, equations. This is a typical equation that we'll look at here next week. Velocity's distance over time. So let's solve this for d and solve it for t. So v is d over t. To solve for d, I have to isolate d. To do that, I multiply both sides by t, and d is equal to t times v. So distance is equal to time times velocity. If I want to solve for t, I take our initial equation. And if I want to solve for t, actually I can just go ahead and get to this point and be quicker. So t is equal to v, t times v is equal to d. Now if I want to solve this for t, I divide both sides by v, and t is equal to distance over velocity. So I can solve them for any variable, and that's a good skill to have when you're trying to solve physics problems. Okay, measured and calculated values. A measured value is always something that we get when we have a device that does the measuring. Now there's always going to be bias, or there's always going to be things that we don't see. So inaccuracy of measurements, uncertainty in measurements, and the factors that can cause this, as you can read, limitations in device, limitations in us, our eyes, and limitations in our skill of actually making the measurement. Now, we have to account for this two different ways. The first is accuracy. Accuracy is how close we are to what it actually is. Precision is how close together different measurements are to one another. It's the old adage, measure twice, cut once. Precision is measuring, and getting the same every time is very precise. How close it is to the actual value is accuracy. So let's kind of demonstrate what all this means. So these are yard darts. Can't play with them anymore. You may put an eye out. But this is good talk about between accuracy and precision. So the game is you're trying to throw the yard dart into the circle. So if we throw 3 darts into the circle, they're close together, good precision. Close to the inside the circle, good accuracy. So this is good both ways. Here we have all 3 close together, good precision. But they're far away from our target, poor accuracy. Here they all are in the circle, good accuracy, but they're kind of scattered about inside the circle, fair precision. Here is probably a poor thrower. Not only are the throws too long, one short, which means we have poor precision, but they're not even close to the circle, which means poor accuracy. So accuracy is how close you are to the measured value. Precision is how close your measurements are to each other. Now, how do we indicate accuracy mathematically? We use significant figures. And again, this should be a review from what you did in chem. But remember the sig fig rules. All non-zero numbers are significant. That means they count as sig figs. Zeros located between non-zero numbers are significant. So for example, 1, 2, 3 are significant. If we have 103, since the 0 is sandwiched in between the 1 and the 3, it also is significant. Trailing 0 are significant only if there's a decimal point. So let's say, for example, we have 100,000. Those zeros are not significant. But if we have 100,000 with a decimal, now they are. So zeros at the end, trailing, are only significant if at any point in the number there's a decimal point. And lastly, zeros to the left are never significant or insignificant. So even if there's a decimal, so if we have 0.0001, these zeros are not significant because they are to the left. The only way we can have numbers be significant is if the zeros are to the right after a decimal. This would have 3 sig figs. Make sure you do the practice on sig figs. Now when we multiply and divide sig figs, the number of significant figures in the answer is the same number of significant figures as the least accurately known input value. So if I took 5.0 times 4.25, and I get my calculator out, I'm doing that right now, 5.0 times 4.25, I get 21.25. That number has 2 sig figs, this one has 3. I want to go the least accurate, which means I will round this to 2 sig figs. So I'll round here. So I will round my answer to 21 because I only want 2 sig figs in my answer. So here's an example. A tortoise races a rabbit by walking with a constant speed of 2.51 centimeters per second for 52.53 seconds. How much distance does the tortoise cover? From our example to start here, distance, all right, distance is equal to velocity multiplied by time. So our speed or velocity is 2.51 centimeters per second, and our time is 52.23 seconds. And I do the handy dandy math with this. 2.51 times 52.23, and I get 131.0973. This has 3 sig figs, this has 4. I want to round to 3 sig figs, so I want to round here. My answer is 131 centimeters, because I'm rounding the 3 sig figs. Addition and subtraction. So the rule is based on how we line the numbers up. And it's equal to the smallest number of decimal places in any of the input values. So if we took 5.01 plus 6.3 plus 10.525, and we add all these up, we get 5, we get 3, we get 8, get 11, get 21.835. We round to the least number of decimal places. So this has 2, this has 3. I want to round to 1 decimal place, so I'm going to round here, and I round this to be 21.8. So it's best to line them up, or look, if you have a long line of ones on your calculator, just make sure you know which one's the least decimal place, and that's what you round to. Scientific notation. Scientific notation, if you call, is a number, the decimal, and then numbers after it, times 10 to some power. When we use scientific notation, the bigger this number, the bigger the number is, right? The bigger x is. If it's positive, it's a big number. If it's negative, it's a small number. So, for example, 3.12 times 10 to the 5th is 3.12, and I move my decimal 5 to the right. 1, 2, 3, 4, 5. And it's 312,000. If it's 3.12 times 10 to the negative 3, I go to the left. 1, 2, 3. 0.00312. So positive exponent, big number. Negative exponent, small number. And we move the decimal place that many. Graphing relationships, understand that if we graph data and get a straight line, just like this, we call this a linear relationship, which means it's called a direct relationship, which means, in this instance, as we increased our time, our speed increased also. And it increased linearly. So the slope would pretty much tell us what our distance was. Now let's look at a parabolic graph. In a parabolic graph, things are a little different. We're talking about squares here, right? And not to get too much into the math, but x is equal to a constant times t squared. So we have what we call increasing. Okay, but it's not a direct relationship, but it's an increasing relationship, which means we are speeding up in this case as time increases, so is our position. So that means we are accelerating. And then the last type of graph is one that has a negative slope, and we call these inverse graphs. And what that means is, as volume increases, we go down, which means pressure decreases, and vice versa. So it's an inverse relationship. As one goes up, the other goes down, and that's what a negative slope graph will give us. 2 other terms that will come up, vectors and scalars. A scalar is just a number. So for example, ice cube at negative 10 degrees Celsius, or the speed of a car at 25 meters per second. Speed is a scalar quantity that describes motion. Vectors, on the other hand, have a direction. So vectors not only tell us the number, but they tell us the direction. So if we say 25 meters per second, normally a direction's given. North, south, east, or west, left, right, whatever. But there's a direction which makes it a vector. Velocity is how we describe motion with vectors. Speed and velocity are 2 terms that'll come up a lot here next week.